Recording is rolling. Welcome to Thursday, December 9th. We're going to start the midterm review today. This is going to last a few days. So here's the format of the midterm. It's going to be in two halves. The first half is going to be 50 multiple choice conceptual questions that I'm drawing right off this review page that I gave you guys. There's 99 questions here. 50 of those are going to show up on your midterm and count for half that. So those are going to be 1 point each. I'm also going to ask you guys 10 multiple choice problem solving questions. There's going to be worth 5 points each, so that it adds up to 100 points total. Like 50 here, 50 here. Okay? And over the next few days, I'll do a thorough midterm review with you guys. Make sure that like anything that I ask, I will have reviewed somehow. Right? But I'm always trying to ask you guys challenging questions, but I'm never trying to like trick you or ask you something that you've never seen before. Obviously, right? Let's have this midterm as open notes. Reason being that this class is more about like critical thinking and thinking creatively and application than it is like memorizing straight values. Even at AP, of course, lets you use this page on the exam too. When you guys walk in today, there's this pack of pages stapled on your desk. Now, I only have so much printing budget, so I have to use this for all my classes. So this is just a class copy, okay? So I'm using this for all my classes for the next couple of weeks. But you guys have all the papers in this packet. Okay, let me go through these. So there's, of course, the AP formulas. There's this side of the AP formula page that don't reference very often, but there's some useful stuff there. So the trigonometries and constants. I gave you guys a page with all the variables, what they stand for, the units they're measured in, some extra notes. 2 pages of those. There's this review page that tells you section by section what would give away that it's like that context, like that framework of thinking. Like, how do you know it's going to be a conservation of energy question? Well, things are like changing height, changing speed, pushing around. There's a spring. Right? What are some good formulas for each section? What's a pretty fundamental example, and what's a pretty fundamental graph? Right. So all these pages. So this will be on your desk next couple of weeks, and also during the midterm. You guys can access this. But again, just got enough for class copies. Okay. Oh, yeah, sorry. Where else can you find these? So I did give you guys each of these pages on the very first day of school, way back in August. So if you kept track of those pages, you might still have them. If not, you need a new copy. Then I did upload all these files also to Google Classroom, so you can access those there too. Download them, print them out. You guys remember that your chapter 8 questions I'm going to pick up tomorrow. Now, some of you guys have already turned these in. We've gone over all the ones that they assigned. So those are due tomorrow if you haven't turned those in yet. I'll put in those points over the weekend. And your guys' rotational dynamics quiz, like this, or the bear and the goodies, space station. This is due Monday. Yes, you guys may have finished this already. Yeah, you can always turn that in early. There is one question on this that I was looking at thinking, I wish I had covered it a little bit more completely. So going back to the chapter 8 questions, one of them that I have not assigned to you guys, but I really like this question, and I really had meant to hit this, just hadn't found a good time in the last few weeks. Okay, so last thing you do for rotational dynamics, we're going to look at number 44 from your textbook, and then after this one, I'll go pretty complete with rotational dynamics, and we'll go into the midterm review after this. So it says 4 objects: a hoop, a solid cylinder, a solid sphere, and a thin spherical shell. Each have some mass, some radius, and they're say rolling down an incline. Now there's a multi-part question there, but I want to ask the question I want to ask. Actually, 2 questions. First of all, who wins that race? And second of all, what actual speed is each one crossing that finish line? Okay. So yeah. Okay. Get a picture drawn here. Get an incline going. Okay. Shouldn't be something weird to this. So it makes more of like a half tight setup. So all down like that. All right, now let's put, sorry, I zoom out for you guys. Let's put 4 Rolly objects here. I'm going to have a ring, But hey, maybe like this right here. Going around. Let's go with basketball, which kind of like the ring has all its mass sort of like on the surface, right? Let's go with a solid cylinder, like a little Flintstone wheel. Kind of like this right here, just rolling. And let's go with a solid sphere, which I'm going to represent with a bowling ball. Right, and those four are in a race down this incline. Throw a finish line down here. So first question, who wins that race? But follow-up question is, suppose I got a guy down here with a radar gun stand on his grassy knoll. What is the linear speed of each of these objects as it crosses the finish line? And so each question. Okay. I'll tell you guys what, the mass of each object and also the radial size end up not mattering. So if you had, say, like a little tiny marble and a big old bowling ball, each solid spheres, those should tie, like win the race. Like, if I have, say, like this big old solid cylinder versus this little tiny solid cylinder, these two guys would tie. Okay. What is important is the distribution of the masses. So out of these four objects, there will be first, second, and third, and fourth. What might have something to do with this is, you guys remember this table from the book, page 257, rotational inertia? Hey, here's those four objects right here. Boom, 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 boom. Right? So we got mr squared for the cylindrical shell. We got half mr squared for the solid cylinder. We got 2/5 mr squared for the bowling ball and 2/3 mr squared for the basketball. So label these I equals 2/5 mr squared, where m is the mass and r is the radial size of that object. Okay. Solid cylinder is 1/2 mr squared. Basketball is 2/3 mr squared, and the ring is just plain mr squared. Okay. So I have put these in order. Like they're going to finish the race something in that order, either 1, 2, 3, 4, or 1, 2, 3, 4. It's going to be one or the other, because I got 40%, 50%, 67%, and 100% of mr squared. Something to do with that. Let me see show of hands what you guys are thinking. And I'll narrow it down to either the ring or the bowling ball. Who's going to win this race? Because one of these guys is going to be the winner, and one will be the loser. Who's going to be the winner? How many guys think the bowling ball is going to win the race? Who says the bowling ball? Oh, look at you guys go. Okay, yeah, you guys learned this section very well. Very nice. Because it has the smallest rotational inertia, which means that it's the easiest to get rolling. Right? You guys remember I passed around this meter sticks a few weeks back? One had masses very close to the center. It was really easy to change its state of motion. Probably really easy to get it rolling if it was like taped to the hula hoop, I guess, right? And the other one had masses scooted really far out. That one was like really hard to change its state of motion. Had a lot of rotational inertia. This ring would take forever to get rolling. Let me simulate an animation. Can you guys imagine animation? Here's what each of these objects are doing. Here's the ring. If there's no friction losses, you could do that for 1,000 years. Here's the basketball. Ooh, a little bit faster. Here's the solid cylinder. Ooh, a little faster. Here's the bowling ball. Zoom, 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 zoom. Okay, now, of course, I'm hugely exaggerating that, but you guys get the idea. Okay? What if you want to answer the question, what is the actual linear speed? Like this sketchy guy on the grassy knoll here, he's got this radar gun. What's the radar gun reading? That'd be like the linear speed, right? What framework do you guys think is probably the most efficient way to solve this question? Conservation of what? Energy. Yep, conservation of energy. I'm going to say sum of energy initial equals sum of energy final. Suppose you got an FRQ that was pretty similar to this. I bet that right there would be worth the point. Like, oh, you have conservation of energy. Right? Although you could solve this another way too, but this is the easiest way to solve this. What kind of energy at the very top? Potential energy. So say MGH, and that'll be true right, regardless of the shape. Right? So something to do with this height change right here, right? This height change, right? Which, as a side note, If you want to make this a little bit more complicated, you might be given what is the length of the incline and what is the angle theta that it's pitched at. Do you guys remember how to get h based on L and theta if it came down to that? You guys see like a nice right triangle right here? Is h equal to L times what? Sine theta. Yeah, h is equal to L sine theta. If you had to do that extra step. Okay. Anyway, here's the source of energy, mgh. Okay. Now, by the time you get down to say the second point here, say crossing this finish line, okay, where's that energy gone? Kinetic. And there's two kinds of kinetic now. There's your translational kinetic, 1/2 mv squared, okay, which if that was the whole actually what this could apply to is an air hockey puck on a frictionless surface. You do that, solve for v, you'd get square root 2gh, and you'd be done. Okay? But we have Rayleigh objects, so I'm going to say plus because some of the energy is going to divert into rotation. Okay? And if you have static friction, then it can still be conserved. They could roll back and forth for 1,000 years. But, what's the expression for that? 1/2 what?
I w omega squared.
Boom! 1/2 I omega squared. Right? You guys see that? Okay, so here's the source of energy at the top of the hill, and here's the two places it goes by the time it gets to the bottom, into moving with some linear speed, but also rotating about its own central axis. But you know what? This I right here, well, isn't there a mass value embedded in it? Right? Now, a little bit different expression for each shape, but this m is somehow embedded in this I. And you know what else? How fast it's rotating and how fast it's moving also related to each other, right? I'm saying this v and this omega are somehow related to each other. I bet we could actually add these two terms together if somehow we could compare that. Right? Let's say that I pick let's pick the bowling ball because the bowling ball is going to win this race. Right? So let's focus on the bowling ball. Let's make some substitutions. So I'll leave the 1/2 mv squared like it is because if the question is what's v, maybe I want to hone in on that. Okay? But I'm going to substitute out instead of I'll substitute in this right here, 2/5 mr squared, because this would be I for bowling ball, right? And then omega, what is omega in terms of v again? V over r. And the fact that it's being squared, I'll go ahead and also square it right here. So v squared over r squared, just take that whole omega squared term and piece and sub that out. Okay, you guess that? Right. Now, this is the expression for the bowling ball. If you had one of these other shapes that you could pop in something else for I, guess that. Now, I'm not going to finish this whole thing with you guys because the rest of this is basically algebra, but I do want you guys to see a couple of things here. We're also solving for this v, right? So this v and this v. Okay. Do you guys see that this r squared and this r squared are going to go away? Okay. Remember how I said the radial size ends up not mattering? Well, there's where it goes away, right there. That narrows it down to 3 terms. Well, it's still 3 terms. Okay. Hey, what do all 3 terms have in common that therefore cancels out? Mass. Now that we did this substitution, see how it hits? So this m. Goodbye. And gravity matters, the height change matters, and something to do with the distribution mass. That's where this 2/5 came from. But you guys could solve for v from there, couldn't you? Bet you could. All right. Now we are definitely complete with rotational dynamics. I told you everything. So back to midterm stuff. So did this page with you guys. A question I get pretty often is what grade would you need to on the midterm for like some overall grade, something like that. Right, so this is for all your classes. Everybody's midterm is going to be 20% of their overall grade for the semester. So you can apply this for every single class with the midterm. Okay? So it goes 40% of your quarter 1 grade plus 40% of your quarter 2 grade plus 20% midterm is your overall grade. Adds up to 100 points. Okay. If you want to simplify that a bit, you could say everything from August through the semester, just regular grades, is 80% of that plus 20% midterm is overall. Okay, so let's pick up from this one, a little bit simplified. Okay. And let's say you have some target grade. Now this number here could be like 90% for an A, 80% for a B. Okay. What would you have to score on the midterm? Hey, could you treat this kind of like X and solve for X? Do some algebra. Get down to this line here. midterm score that you need ends up being 5 times what you want minus 4 times what you have. For example, let's say in some class you have a 77. You're like, I wonder if I could get a B, which would be like an 80. Well, really, it's like a 79.5 because it's kind of around that, but something like this, right? So put in your target grade here. I'd really like to get a B in that class. I'd really like to get an 80. I have a 77. So 5 times what you want minus 4 times what you have, and then that's what you would need on the midterm to get that.
Can you say our current grade is that with just quarter one and quarter two?
Yeah, that's quarter 1 and quarter 2, like the average of those. Yeah, quarter 1, quarter 2 average. Yeah. There you go. Guys for that?
Wait. I need to picture this.
Yeah, that would be a good photo right there, right? All right. Recording this too, so if you guys want to watch this video later when I upload it. All right, then here's the midterm schedule, also posted to Google Classroom. Your first midterm on Thursday is period 7. Then Friday is going to be 1 and 6. Monday, 2 and 5. Tuesday, 3 and 4. And then Christmas time. Next week, I'm not going to be here on Thursday because jury duty. I really hope that's a one-day thing, but time will tell. All right, let's get to this midterm review. What we're going to do this is I'm going to go over these 99 bullet questions one by one. Again, 50 of these are going to show up. Understand? And along the way, I'll do some extra example problems with you guys, some graphs, some equations. Make sure that I do a really comprehensive review with you guys. All right, so top here, when you look at the speedometer of a moving car, you can see that car's what? Yep. Oh, yeah, go ahead.
How did you get the 99 questions?
Yeah, we don't have a 99.
Okay, so real fast, who needs the 99 questions? Who else? Pass one of these back. Pass one of these back. Pass them back. Guys, okay.
Are you recording this? I was just gonna ask
Yeah. Yep, recording. Yeah, so look at the speedometer of a moving car. You see that car's instantaneous speed. I told you guys the midterms over notes, right? Okay, so train travels 6 meters in the first second. Travel 6 meters in the second second. 6 meters in the third second. What's the speed of that train? 6 meters per second. But that's not the question here. The question is, what's the acceleration of the train? What's the answer to that question? 0 meters per second squared. Because acceleration is a rate change of velocity, and this train has a constant velocity. Oh, yeah.
What was number 1 again?
If you look at the speedometer of a moving car, you see the instantaneous speed, like how fast you're moving at that moment. Can you guys see like a speedometer needle like pointing up, like 30 miles an hour? Car starts from rest, and after 7 seconds has picked up to 42 meters per second. How many meters per second was it picking up every second?
6.
6. 7 times 6 brings you up to 42. Okay. Which maybe makes you think, maybe we need some equations, right? Let's break out those equations. Now, these are, of course, on your reference pages, but it's good to memorize anyway. You guys know x equals v naught t. Now, if there's no acceleration, that's the whole story. This is the speed times time. If you are accelerating, it could be 1/2 at squared if you start from rest. And if you start with the speed and you're accelerating, you just add them together. We got the speed you pick up, or I should say the velocity you pick up to, is equal to the velocity you start with, plus a times t. And velocity final squared equals velocity initial squared plus 2 times acceleration times the displacement. Okay. And the third one's pretty closely related to conservation of energy. Okay. So the one we just applied was the second one right here. It said start from rest, so v naught was 0. Got up to 42 meters per second. It took 7 seconds. 42 divided by 7 leaves you with 6 meters per second squared. As an object falls freely in a vacuum, does its velocity increase? Yep. Does its acceleration increase? No. Acceleration is constant. And at surface of Earth, that would be about 10 meters per second squared. Okay. As an object falls freely in a vacuum. Okay.
Velocity increases in a vacuum.
Yeah. Let's do a graph for that. Let's do a graph for, let's see, let's say you fall off cliff. Okay. Let's just do a velocity in meters per second versus time in seconds. Okay. So 0, 1, 2, 3, 4, and then 0, 10, 20, 30, 40. Okay. I'm using, okay. You guys see the second equation right here? You could basically use this, y equals mx plus b. Now, if v naught 0, say it starts from rest, like the word drop, at time 0, 0 velocity, let's call it down positive. After 1 second, you picked up to 10 meters per second. 10 times 1 is 10. 10 times 2 is 20. 10 times 3 is 30. Is that just going to give you, like that right there? Okay. Drop ball off a cliff. Okay. Classic V versus T shape right there. Okay. Now, this is assuming that there's no what? Yeah, no air resistance. Say no air drag. What if, we hadn't done this for a few weeks, but it was either like September, October, somewhere there. We actually went back and said, what would this graph look like with air drag? Actually, I asked you this is one of your quiz questions. How's this graph look different?
Parabola.
Actually, I don't know what shape it would be called, but it's
A
maybe
horizontal asymptote.
right. Yeah, it would have a horizontal asymptote. So somewhere there would be a horizontal asymptote. Now, where that horizontal asymptote is depends on the shape of the object. Like if you have a parachute, I bet it'd be pretty low. If you don't have a parachute, it'd be pretty high up on the graph. What is the name of this horizontal asymptote? VT. Or, sorry,
Terminal.
yeah, that's what I was trying to say. Yeah, terminal velocity. V terminal. Okay. And then this would start off kind of like free falling like a vacuum, but then air drag would pick up and it would eventually reach that terminal velocity like that, right? So this is with air drag. Right? In the absence of air resistance, objects fall with constant what?
Well,
Mm-mm-mm.
acceleration.
Yeah, acceleration, constant acceleration. So the change of velocity is constant, right? The rate change of velocity is constant. I might say the slope of this graph is constant, and that would be acceleration. The slope of this, yeah, you guys remember that. Suppose an object isn't free fall. Each second the object falls, let's say, the same distance as before, or a larger distance than the second before. I'm thinking a larger distance than the second before. Because wouldn't that be specifically be a squared relationship, like this right here? Right? X is related to t squared. So every second. Right? Let's go ahead and do the cliff at this point.
Cameron Rustin and Alyssa.
Cameron and Alyssa. Alright, so let's do drop ball off cliff. Right. Let's define down as the positive direction. Right. And say it starts from rest, you're on Earth. No, basic assumptions, right? I'm going to do a table and some graphs with you guys. Split this in half. We'll put some graphs over here. We're going to do X versus T, B versus T, A versus T. Classic 3 kinematic graphs. Okay. And then let's also do a table. So X in meters versus T in seconds. V meters per second versus T in seconds. Acceleration meters per second squared versus T in seconds. Okay. And then for the table, let's go time in seconds, acceleration meters per second squared, velocity meters per second, displacement in meters. Okay. So time to be ticking along 0, 1, 2. 3, 4, 5. Okay, so time's ticking. Takes a few seconds. Okay. Yeah. Let's do this table first, and we'll go fill in the graphs. Right, so right after you release the ball from your hand, what's the acceleration equal to? On Earth? Yeah, 10 meters per second squared. How about after it's been falling for a second through a vacuum?
10.
10. that's going to be constant, isn't it? That's called constant acceleration. Right? How about velocity? If it starts from rest, say you drop it,
0,
yeah, v naught would be 0. Then it takes up to
10,
10.
20,
Right?
30.
That would be like this formula, right? V naught 0 just v equals at. 10 times how much time it's picked up to. Right? How about x? Here. If it starts from rest, doesn't that just boil down to 1/2 gt squared, 1/2 at squared? Something to do with that. Right? Let's call the top of the cliff point 0 and down is positive. After 1 second, how far has it fallen in meters? It's not 10 meters, it's 5 meters. 1 squared times 10 over 2, 5 meters. After 2 seconds, 2 squared times 10 over 2, okay, 20 meters. 3 seconds, 3 squared is 9 times 5 is 45 meters. 4 squared times 5 is 80 meters. Let's see, 5 seconds. After 5 seconds, how far?
Only 25.
About 125 meters. Hey, that's mine shaft in California, isn't it? Falls for 5 seconds squared. About 125 meters deep. College. Yeah, that's that. Right. So, hey, we could treat this like Cartesian coordinates. Got TA, TV, TX. Right? All right, just plot these. I usually start this with the V versus T, so let's do that one first. Can you guys draw what that graph's going to look like? Actually, we did this one earlier today. Okay, it's just like that, right? And what's the slope of this equal to? 10 meters per second squared. G, right? How about the A versus T? What does that look like?
So it's horizontal.
Yeah, this horizontal line at the gravity field, 10 meters per second squared. Okay. This is all in a vacuum, of course. Okay. How about X versus T? Parabola. I'm going to define the top of the cliff as 0.0. So at time 0, it's at 0.0. And then if down is positive, it will take this shape. Right? So the question that prompted me to draw this graph was each second it falls further than the previous second. So see how during the first second it falls 5 meters, then after that 15, then after that another 25, then like 35, right? Keeps like picking up. Okay. Yeah, that will make a parabola shape. Okay. Guys, get so far? Ball tossed vertically upward, rises, reaches highest point, then falls back to the starting point. During this time, the acceleration of the ball is always which direction? Down. Yeah, down. Okay. Now, when it's moving up, its velocity is up. When it's moving down, its velocity is down. Whatever its direction of motion is same as direction of velocity, right? Positive or negative. But acceleration is the same direction as the net force, which is always down because its weight is straight down. Anything in free fall, the only force acting on it is its own weight. It has to be down. Okay? Hey, when the ball's moving upward, is it speeding up or slowing down? Slowing down, and then moving down, or it's speeding up? Okay. Let's think about the signs of these things. You guys remember if it's moving up, velocity is up, but acceleration is down? And if it's moving down, both velocity and acceleration are down? Okay. And anytime those two, velocity and acceleration, have the same direction, it's speeding up, and if they have opposite direction, it's slowing down. Remember that too? Ball's thrown straight up. At the top of its path, its instantaneous speed is what? 0 meters per second. Ball's thrown straight up. At the top of its path, its acceleration is what?
10.
10 meters per second squared. Yeah. You know what that sort of reminded me of is, let's go back to this cliff, but instead of dropping the ball, let's throw this thing. Let's say throw ball, let's say upward from edge of cliff. I'm still going to have down as the positive direction. Now, AP could go either way. They usually define it for you, so they might say like up is positive, but I'm going to have downward. And then we'll do a second scenario, throw ball downward from the edge of cliff, down is positive, so vacuum, earth, that whole thing. pick those three graphs: x versus t, v versus t, a versus t. Right, so first scenario, you throw the ball upward, but remember if down is positive, that means you threw it which direction? In the positive or negative direction?
Negative.
Negative. So at time 0, you'd have to have what, positive or negative intercept on the v versus t. Negative. Yeah, here's your v naught right here. Now that's 1 point on the v versus t. Okay. What does the rest of that graph look like? Can you guys draw the rest of that graph?
Is it just a straight line going up?
That's what you guys just drew, right? Okay. What's the slope of this equal to?
Acceleration.
Yep, the acceleration. 10 meters per second squared, call it g, Earth gravity. Okay. And there must be something special going on here. What's going on right here?
It's
at the peak.
at the top.
Yeah, it isn't the peak. Because it says 0 velocity. It is at the peak, isn't it? Okay. Let's see this graph. Acceleration versus time. What does that look like?
Horizontal line.
Yeah, horizontal line. At the value g, like 10 meters per second squared. If you only knew acceleration, would you ever know where the peak was?
No.
No, you have no idea, right? It's always accelerating down 10 meters per second squared. How about x versus t? Can you guys? I'll give you guys 1 point. Let's say the top of the cliff is 0.0, so that point exists. Okay. Yeah.
It's like a parabola, but it goes down a bit and then up.
Exactly. Yeah. It's gonna be a parabola shape. Acceleration x versus t. Now remember how this is a very special time? It peaks right there, and this whole graph's gonna be upside down of what it's actually doing, right? Because down is positive. What part of the parabola is at that time?
Bottom.
Minimum.
Yeah, bottom, minimum, vertex. You guys were thinking. So let's say it takes us like a second to reach the peak, take another second to fall back down to the original level, and it's just gonna continue on like parabola style, like curving. Okay. Yeah, that is a parabola. The vertex right there. Okay. You guys good there? Now, if you throw the ball downward, right, start with v versus t. If you throw it downward into positive territory, isn't it already moving in the direction that's towards? And then the rest of that graph looks like what? Isn't it the exact same slope as before? Okay. Same slope. How about a versus t? What does that look like?
Just a horizontal.
Yeah, exact same graph. These two graphs are identical. So if you're just looking at acceleration, you don't really know the direction of motion, do you? Oh. How about x versus t? What's that one going to look like?
Are you still starting at 0?
Yeah, let's do that. Let's have the cliff edge at 0.0. So that would be a point on the graph. That's true. Then what? How about this? When you threw the ball upward, remember how to go up, peak, and then come back down, and then past the point where it started, and then it's still a piece of a parabola. It still curves. It's kind of a shallow curve.
So is it just that part?
It is. Just take this, go copy paste that right there. This is gonna curve just like that. So this is a piece of a parabola. I'm gonna label it that because it may not be super obvious because the vertex is not even on the page. Okay? Mathematically, the vertex would be like in the past. Are we here? A car accelerates at 2 meters per second squared. If the car starts from rest, how much time did it take up to 20 meters per second?
10 seconds.
10 seconds, right? 2 times 10 is 20. Okay. That is, where's my formulas? That's this one right here. Starts from rest, this is 0. 2 times 10 is 20 meters per second. If a freely falling object were equipped with a speedometer, or what I say is if you point a radar gun at it, or a motion detector, API motion detector, its speed reading would increase each second by how much?
10 meters a
Yeah,
second.
10 meters per second. Just did that. A freely falling object starts from rest. After falling for 6 seconds, it will pick up to a speed of 60 meters per second. Right? 6 times 10 is 60. a ball's thrown into the air at some angle. Wait, hold on. Actually, we're getting into the projectiles. Let me make sure I've covered all the linear stuff. Throw you guys one more scenario, because all the linear stuff we've done so far has involved time. But I can throw a scenario at you guys that that bypasses that. So, what if you have a cliff of known height? And give us a height. Let's say the height is say 45 meters. Okay. And you want to know if you release the ball from rest, how fast is this thing hitting the ground? Plus the what is that? And one more thing, say gravity is 10 meters per second squared. Okay. Could you guys use that? See how I didn't say anything about time? Right? Now, you could solve it that way. You could figure out how much time it takes. But could you also say v final squared equals v naught squared plus 2ax? Okay. Or you could also use conservation of energy, couldn't you? We haven't got that part of the review yet, but I'll show you guys. V naught is 0, so this piece goes away. Solve for VF. In terms of variables, isn't that just square root 2ax? Hey, does that look a lot like square root 2gh? Yeah, which is expression that shows up pretty commonly. Conservation of energy did too, right? Square root 2gh sort of deal. Okay. So square root 2, 10 meters per second squared for 45 meters. I know what this is going to come out to. It's got to come out to 30 meters per second. Let me confirm that though. Here we go. Square root 2 by 10 by 45. Yep, 30. How much time to hit the ground? Here, I just stole that from here. If you edge of a cliff, drop a ball,
3 seconds.
45 meters, takes 3 seconds to get there, going 30 meters per second. That's fine. Here, okay. Second. How about, let's go to another cliff. Let's say you're on an alien planet. Give this guy a little astronaut helmet. Alien planet. Okay. And you know the height of this cliff. Let's say height is 100 meters. And you time this thing with a stopwatch. And the time is like, let's say it takes 10 seconds to reach the ground. Now, 10 seconds to fall 100 meters. I'm thinking the gravity's what? Really strong or really weak on this planet? Yeah, really weak. It's taking forever for that ball to reach the ground. I wonder, what is the gravity field on this planet? Let's try this. Maybe x equals 1/2 gt squared. Starting from rest, it boils down to that, right? 100 meters, 1/2 g, took 10 seconds, squared. 10 squared is 100, divided by 2 is 50. Divide 50 over, I think that's 2, right? Did I do that right? 2. Yeah, that's right. Yeah. Oh, actually, that's not too far off from the moon. Moon gravity is pretty close to that. 1.6. Ball is thrown to the air at some angle. At the very top of the ball's path, its velocity is entirely what? Yeah, horizontal. Yeah, let's draw that up. You guys can see that. Ground, ball, initial velocity. Notice that's off on some weird angles, so that's not vertical or horizontal itself. But maybe that's like throw speed. Gonna go into like a parabola shape, right? But at the top of its path, wouldn't its velocity be sub x, like entirely horizontal? Would that be true? Okay. Do you know what? Wouldn't that horizontal component velocity be true for the entire trajectory? However fast it's going across the field, it's always going that speed. Is that true? Okay. If you knew the angle that you threw this at, say relative to the horizontal, call it theta, how could you solve for Vx? isn't this also v sub x here? And it stays that way because this ball is not accelerating horizontally. It's accelerating vertically because there's a gravity field there. No, that it only pulls vertically. Okay? But horizontally, it has inertia. Just keeps doing what it's doing all the way across. What is Vx in terms of V naught and theta?
Cosine, cosine.
Cosine. Yeah. Cosine relationship. You see that? Remember that? Okay. Actually, you know what? While we're talking about a little bit of trigonometry review, let's hit that a little bit. What if I'm just gonna ask you a question I asked you guys earlier, which is if you know the length and you know theta, can you solve for height, like a height change? Say you're like pushing a box up and you're like, how much work does it take? Right? That height change might be really important. So do the MGH, right? But you guys would tell me that H is equal to L times what?
Sine theta.
Yeah, L sine theta. So you guys got that. What about this? What if you know? Actually, some of the questions I got are coming up here pretty soon. So, yeah, hang tight on that. Okay. Number 14, a ball thrown in the air will never go as physics ideally would predict because. Right, let's go back to this. Okay. So you could do some projectile calculations on this. You could say, well, I know how fast it's going across. Hey, do you think you could find this vertical component called v naught in the y direction? And then that would constrain the amount of time it would be in the air for. And then if you knew that time, you could take that time multiplied by v sub x and get x like the range. Okay? That's called range equation, which we've done that way back in the day. But you could calculate this all day, and then we could go outside. We could actually throw some balls, and they're always going to land a little bit short. Why? Because what are we usually ignoring in this class? Air drag, yeah, air resistance, yeah. So air friction. Here's the one. An airplane flying into a headwind loses ground speed. So the plane's flying north and the wind's blowing south. It's going to slow down relative to the ground. Airplane flying with the wind gains ground speed, right? The plane's flying north and also being pushed north with the wind. It's going really fast compared to ground speed. What about an airplane flying at right angles to the wind? What is its ground speed compared to, say, still air? What would the speed of its shadow be across the ground? Plane flying straight north, let's say at 80 kilometers per hour. That's what its engines can do relative to the surrounding air. And then it runs into a crosswind blowing straight east. So it's a pretty good crosswind going at 60 kilometers per hour. Notice how I connected those vectors tip to tail. You see tip to tail? Plane's always pointed north, wind's always blowing east everywhere. Connect the vectors tip to tail. Then I can create a resultant going from the tail of the first vector to the tip of the last one. Now, there's 2 vectors here, but if I had like 10 vectors, I could do chain on tip to tail. This is called the resultant. Okay. And this resultant vector has both a magnitude and a direction, like all vectors do. So let's start with the magnitude. What is the magnitude of that resultant vector?
100.
100. How'd you guys know it was 100?
3, 4, 5.
It is a 3, 4, 5 right triangle. Yeah, if you saw that proportionality, proportion of legs is 3-4 ratio. Scale up by a factor of 20. Is that? Pythagorean theorem. 60 kilometers per hour squared plus 80 kilometers per hour squared, square root of that. That's Pythagorean theorem, isn't it? That is 100 kilometers per hour. That's how fast the plane is moving relative to the ground. That's how fast its shadow is moving across the ground. Okay. Oh, so the answer is it's actually going faster than its engines were originally propelling it. Okay? That's the answer to the question. It's going faster. No, it's not faster in the direction it's trying to go. It's kind of going off northeast, isn't it? And that's the other part of this question is, what is this angle theta? Do you guys remember how to extract theta from sides of a triangle? We have a right triangle here.
Use the inverses.
Yeah, some kind of inverse trig. Right? I'm gonna play off inverse tan. I like to use that one. Theta is equal to inverse tan of whatever what. Exactly, opposite over adjacent is 60 over 80, right? Kilometers per hour, kilometers per hour. The units cancel out. Okay. So remember, sine, cosine, or tangent of some angle will give you some ratio. Inverse sine, inverse cosine, inverse tan of some ratio will spit you out an angle. Okay. Does anybody happen to have memorized what this angle is for a 3, 4, 5 right triangle?
Wasn't it like 53,
Yeah, this one up here is 53,
53,
and this one's
whatever the rest of that
Yeah.
is.
37 degrees. These two, the two acute angles have to add up to 92, right? Okay, let's try this out. Inverse tan, 60 onto 80. 37 degrees right there. Yeah, nice. Let's remember that. Yeah. What is the resultant of a 3-unit vector and a 4-unit vector at right angles to each other? 5 units. Yeah, which is pretty much exactly what we just did. Scaled up by a factor of 20. Okay. 3 times 20, 4 times 20, 5 times 20. 3, 4, 5. When in orbit, a satellite such as the space shuttle is, the one we're looking for here is simply a projectile. This set of materials that I drew these questions from, actually these are Paul Hewitt questions in conceptual physics. This is the only projectile question that I remember having in these stuff that does involve a curved surface. Because all these other projectiles, we've been assuming basically like a flat surface, which is true locally. But yeah, if you get going fast enough to like 8,000 meters per second, you actually could overcome the curvature of the Earth via a special kind of projectile. Okay? I've got another projectile question for you guys. And it's one of the lab. The lab that had you guys do back with projectiles. You guys remember you had those spring launchers, and we went out to the balcony, and you guys aimed this. This was one setup you could have done. The question was, what's the blast speed of the launcher? And one of the pretty straightforward setups would have been, called speed blast, to aim it straight horizontally at the top of this balcony. Okay. I want to say the balcony was about 4.5 meters tall, something like that. I'm going to round that to 5 meters. Let's say height is like 5 meters tall. Okay. And then you spotted where the ball landed. Call that some distance x. Oh, hey, that's a piece of a parabola right there, isn't it? With the vertex right at the launcher. Call this distance x. Let's say that came out to 11 meters. Right? You'd have to know one more thing to solve for the blast speed. One more piece of information, and that is Earth gravity. So let's call that 10 meters per second squared. Okay. One of the things I want you guys to get from this class is to be able to look at a problem and sort of like intuitively be able to figure out what variables would be important, or even play around with those variables and think how that would change the situation. For example, if you took the same launcher to the moon, which has really weak gravity, would it land shorter than or further than 11 meters? Way further. It's going to go pew, like way out here, right? Even for the same blast speed. Okay, so this is an important variable. That's how that would factor. Okay, so what is this blast speed? Well, that's sort of like a horizontal type question, isn't it? I know that V blast would be, if I just focus on the horizontal stuff, well, it went this far, 11 meters, in some amount of time, right? Distance over time. If only I knew how much time it took to get from here to here. How do you do that? Well, that has something to do with the vertical stuff, doesn't it? Okay. And that was the trick with projectiles. So sometimes you had to shot horizontal to get vertical, or in this case, vertical to figure out something that's horizontal. Right? So I have to ask another question first, which is how much time does it take to fall 5 meters? Yeah, 1 second. 1 second. Yeah. Because you guys remember x equals, here, it's v naught t plus f e t squared, but I can just boil it down to this. Okay. Why did I leave off the v naught t part? Because in the vertical direction, when this ball is leaving this launcher, how fast is it moving up and down? How fast? Meters per second. Yeah, 0 meters per second. No, it's accelerating down immediately at 10 meters per second squared. But yeah, so v naught in the y direction is 0. That's why I left off that piece. Right. So to fall 5 meters, picking up at 10 meters per second squared, yeah, t does end up being 1 second, okay, to fall 5 meters. Okay. It's also back to the cliff. You guys remember 1 second falls 5 meters? Okay. Yeah, did you guys remember that? Okay. So take that, pop that right there. Blast speed for this example would be 11 meters per second. Yeah, that's it. You guys can solve that one. Yes, sir. After a cannonball is fired into frictionless space, the amount of force needed to keep it going equals how much? 0. Yeah, law of inertia. Okay, so we're on to Newton's laws now. Newton's laws, forces. Yeah. So the only reason anything would ever speed up or slow down for that matter is if there's a what acting on it? Force. Yeah, if there's no force, then inertia, just keep on going. So avoid your spacecraft. Just keep on going. If the force of gravity suddenly stopped acting on the planets, they would, can draw this one out. So let's get the sun going. Okay. Get a planet in an orbit that's, say, approximately circular, but a little bit elliptical, right? At some point, maybe the planet's passing out the like P for planet. Okay. And does this planet have an instantaneous velocity that's like this direction, called v velocity? Okay. If I hold my roller flush to the orbit, I can create what's called a tangent line. And you guys, if you're taking calculus, that's a term you see all over the place, right? Like a tangent line. It's important for like instantaneous rate changes. Okay. So we've got an instantaneous velocity that way. Now the sun is pulling inward. Gravitational force is acting as a centripetal force, like pulling it in. Okay. But what if you turn that gravity out? Just boom, turn off gravity right at that moment. Would the planet keep on going in that direction, or would it make a random 90-degree turn and go immediately away from the sun? Which way? Yeah, keep going straight. Tangent to its orbit. Yes, and that's law of inertia. Same thing if you have a ball on a string. Going zoom, zoom, zoom in a circle, and then cut the string. Same story. Tangent to its motion. It'll fly out exactly that way. A sheet of paper can be withdrawn from under a container of milk without toppling the milk. If the paper is jerked quickly, because the milk carton has a lot of what? Mass or weight? Mass. In inertia is a property of mass. Right? So like weight doesn't really help because that would press down the paper, would increase the frictional force, would make it more likely to topple. More mass is more inertia. Now, of course, those are directly related anyway. So, but yeah, specifically that property. You guys saw Paul Hewitt with the tablecloth? You guys remember that?
Is that none of the above?
Oh, no, inertia. The milk carton has inertia. Yeah. So if you guys ever want to go watch all those Paul Hewitt videos, I put them all in a zip folder for you guys somewhere on Google Classroom back in the day. The force required to maintain object constant speed in free space is equal to 0. Just talked about that. Okay. Equilibrium occurs when, let's see, all the forces on an object are balanced. True. Some of the x forces and negative x forces balances out to 0. True. The net force on the object is 0. True. The sum of up forces equals the sum of down forces. True. All those statements look true. Now, recently, just in the last few weeks, we added one more condition for equilibrium, and that was what? What else also has to sum to 0 for equilibrium? The torque. Yeah, the torque. Okay, so that's more recent addition. Okay, well, you guys see the next question coming up. Has to do with like a girl hanging from a bar supported by 2 vertical strands of rope, which I had hanging right here, but I moved it to that lab area. So we will pick up there tomorrow.